In this lesson, I'm going to show you how to find the exact primary trig ratios for any angle in standard position on the Cartesian plane. So we will begin by looking at angle theta. And I'm just going to color over the terminal arm for angle theta in green to make this a little bit clearer. So we're looking at angle theta, and we're also going to mark off point P, which could be any point along that terminal arm. Now, I'm going to draw a vertical line connecting point P to the x-axis. Okay, and we can see that by doing so I've created a right triangle, which is going to allow me to find expressions for sine, cosine, and tangent of theta using what I know about right triangle trigonometry and SOHCAHTOA. So if I've marked off point P with coordinates x, y, if we think about that, no matter where that point was located on the Cartesian plane, the lengths of the side of the legs of this right triangle would be x and y. So wherever that point was located, the length of this side would be, well, whatever the x coordinate was, and the length of the vertical side here would be whatever the y coordinate was. Now notice we've labeled the hypotenuse of this triangle with an r. So r is the distance from point P to the origin. The reason I think we use an r for that side is because if we were to rotate point P in a counterclockwise direction around the origin, it would create a circle, and that terminal arm would be the length of the terminal arm, would be the radius of that circle. So that's why we use an r for that side. And we'll get back to speaking more about that circle in coming lessons. For now, the circle doesn't have a great significance to what you're going to be doing today. Okay, so we have our right angle triangle. We've labeled our sides, x, y, and r. Now we're going to come up with expressions for sine, cosine, and tangent. So, looking first at sine theta. Sine theta, we know from before, is the ratio of the opposite side to the hypotenuse. So looking at our diagram, opposite to angle theta, we have side y, and our hypotenuse, of course, is labeled r. So sine theta equals y over r. Cos theta is adjacent over hypotenuse. And from our diagram, we can see the length of the adjacent is x, length of the hypotenuse is r. So cosine theta equals x over r. And tan theta, which we know is opposite over adjacent, will be y over x. Now, if we're going to apply these formulas to find exact expressions, exact values for sine, cosine, and tangent of this angle, we're going to need to find a way to find the value of r. So if we knew the location of point P, that would help us because r, of course, is the hypotenuse of this right angle triangle. So the Pythagorean theorem is going to come in handy in this lesson and in your follow-up questions. Okay, so we could find the length of r using the formula r squared equals x squared plus y squared, or r is equal to the square root of x squared plus y squared. Okay, so this adjusted version, simplified version, we'll say, of the Pythagorean theorem is going to help you find the length of that side in one step. So that was a lot to take in sort of at the beginning of the lesson. Let's go through an example and see if we can make sense of some of this, okay? So this example says P is the point negative 8, 15. And we are asked to calculate, and that's a point on the terminal arm of angle alpha. We are asked to calculate values for sine alpha, cosine alpha, and tan alpha. And we will leave those values in exact form. We won't simplify them. Now, it looks to me there was a formatting issue here when I brought this into my iPad to create this note for you, so don't mind my graph here. I will see if I can fix it. So let's extend this, and I'm not exactly sure what happened there. So it says point P is the point -8, 15. So let's mark that off in quadrant 2. Seem to be having more issues with the writing today. Let's try that again. Point P is -8, 15. And so we'll draw the terminal arm for point P. So this is the angle that we're talking about here. This is angle alpha. And we are asked to calculate values for sine, cosine, and tangent. So let's go ahead first and find out what r would be. In other words, what's the distance from point P to the origin? That would be the hypotenuse of the right triangle corresponding with this angle. So using our formula above, we said r squared, let's use the simplified version of the formula, that would be better. So r is equal to the square root of x squared plus y squared. Let's substitute the known values. So -8 squared plus 15 squared. So r is the square root of 289, which is 17. Now once I have the value of r, I can use that to find sine, cosine, and tangent. Sine alpha, using our formula above, equals y over r. So 15 over 17. The y value, of course, coming from the y coordinate of point P. Okay, cosine alpha is defined as x over r. The x coordinate of point P is -8, so it'll be -8 over 17. And tan alpha is y over x, or 15 over -8. Now in part B, we are asked to calculate the measure of angle alpha to the nearest degree. I could use any one of the ratios that we just figured out for angle alpha to do that. It wouldn't matter which one. So let's use the sine ratio. So since we know that sine alpha is equal to 15 over 17, what I can do is use the inverse sine function to find the value of the measure, of angle alpha. I know that alpha would be equal to sine inverse 15 over 17. And if I type that into the calculator, I find out that alpha is approximately 62 degrees. But look at the diagram that we drew in part A. Alpha is clearly not 62 degrees. Alpha is clearly an obtuse angle. So what's happening here is the calculator is kicking back to you the reference angle, the measure of the reference angle for alpha. So you're going to have to do a little bit of extra thinking here, okay? Because what it's actually telling you is that this angle in quadrant 2 measures 62 degrees. So if the angle in quadrant 2, if the related acute angle, so the reference angle is 62 degrees, then we have to figure out what alpha is by subtracting that from 180 degrees. So let's see if we could write that down. So we'll say, but alpha is in quadrant 2. And what I mean by that is the terminal arm for alpha is in quadrant 2. Okay, just a shorter way of saying that is that alpha is in quadrant 2. So 62 degrees is the reference angle. So as I was saying, we can find the measure of angle alpha by subtracting 62 degrees from 180 degrees. So alpha is actually 118 degrees. All right, then moving on to example 2, I see that we had another formatting issue here. It says that angle beta is in quadrant 4, and it should say, as I believe it says on your handout, hopefully, it should say here, and tan beta, let's see if I can fill it in, is -3/4. So I'm not sure what happened there. All right, so beta is in quadrant 4, and tan beta is equal to -3/4. Our task is to find the values for sine beta and cosine beta, and eventually find the measure of angle beta itself. So again here, I need to fill in the rest of my graph, which didn't come through properly. Okay, what we do know is that tan beta equals -3/4. So tan beta equals -3/4. Now what I know from the formulas is that tan beta is equal to y over x. So y over x equals -3/4. That tells me the positioning of a point on the terminal arm for angle beta. It tells me that x is 4 and y is -3. So if I plot the point 4, -3, that is a point on the terminal arm for angle beta, which is the angle that I'm looking for. Now, if I have values for x and y, then I can find the value of r, because I know that r is equal to the square root of x squared plus y squared. In this case, 4 squared plus -3 squared. Okay, so r is equal to the square root of 16 plus 9, square root of 25, so r is 5. So now we have values for x, y, and r, and I can use those values to find expressions for sine and cosine. So we know that sine beta is equal to y over r. So now I know that will be -3/5. And cosine beta is equal to x over r, which will be 4/5. Now once again we're asked to find the measure of angle beta. So we know that sine beta is equal to -3/5. So beta will be equal to sine inverse -3/5. And so the calculator tells me that beta is equal to -37 degrees. Now we normally wouldn't leave that expressed as a negative angle. Looking back to your diagram, that's telling us that this angle here, okay, has a value of -37 degrees, that counterclockwise angle. I apologize again for the lack of clarity here in the writing, okay, so -37 degrees. We probably don't want to leave that like that, so to express this as a positive angle, see if I can fit this in here. We're going to subtract it from 360 degrees. So 360 degrees minus 37 degrees tells us that beta is equal to 323 degrees. Please refer now to part 2 of this video lesson.